Hi everyone. Today I'm going to talk about the variable selection method change in estimate and how it reacts to different types of measure of effect such as risk difference or odds ratio. To go into specific examples, let us consider a continuous outcome at first and consider that we have a treatment effect of 1.3 for a particular treatment. And the way we have generated this is that we have a treatment A, we have an outcome Y, we have a variable P that has nothing to do with other variables, and we have a confounder variable L that is impacting A, and that is also impacting our Y, and here our Y is continuous. If we generate the data and look at this data, we can see this Y is a continuous variable, L is a continuous variable, as well as A is a continuous variable, right? So we can basically use a linear regression to estimate the impact of A on Y. So that's what basically we are doing here. We are using a GLM with family Gaussian, and we are having our outcome Y and our treatment A as a predictor variable of Y. And we get an estimate of 1.83. But we generated the simulation in such a way that we have 1.3 as our treatment effect, right? As we have described earlier. But L is a confounder. That is why when we are just adjusting for A, when we are trying to estimate without any kind of adjustment, we do not get the treatment effect 1.3. But as soon as we adjust for L variable, we get 1.3 as our treatment effect estimate. Okay. So in the presence of confounding, when we used this method, our estimate of treatment effect changed when we did or did not adjust for L in a continuous outcome scenario. Okay, let us consider a second scenario where we still have a treatment effect of 1.3, but we are now considering a binary outcome. The design remains the same in terms of the DAG. We have a L that is a confounder, and we have a P variable that has nothing to do with the other variables. And then we generate the DAG and the data, and we see the only difference in here is that the Y is a binary variable here. Since this is a binary variable outcome, we are using a logistic regression, and the way we are estimating from a logistic regression is by using GLM with logitlink in the binomial family. And we get an estimate of 1.68, which is not correct estimate because our true treatment effect was 1.3. And then as soon as we adjust for L, we get the correct treatment effect of 1.3. Now, consider the scenario that if we were using a change in estimate method and we were trying to identify whether L is a confounder or not, what we would do is we would try to see whether with or without adjustment of L, whether the treatment effects are changing or not, right? And basically there is a cut point generally used of 10%, and we would generally see whether a 10% cut point is there or not. Sorry, a 10% increase in treatment effect is achieved by adjusting for L or not. And that would determine whether L is a confounder or not, right? All right, so in our scenario of binary outcome, we can see that we have a difference of 10% with and without adjustment of L. That's why we would determine that L is a confounder variable for a binary outcome, right? And so was true when we were considering a continuous outcome. Without adjustment of L, we would see there is a change, and then we would determine that L is a confounder variable. Okay, in our true scenario, obviously L was a confounder variable, and this is giving us the correct decision of whether one should adjust for a variable or not. All right, let us use a counter example. This is a much simpler example where basically the treatment effect is still the same 1.3, But the only difference is that we have a variable R here, which is a risk factor for Y, which has nothing to do with our treatment variable A, right? And in this scenario, when we generated the data and our Y was continuous, we can generally see that irrespective of whether we adjusted for this R variable, we get the same treatment effect estimate 1.3. That means that this R variable is not a confounder, and we do not need to adjust for this R variable to get the correct treatment effect estimate, right? Whether or not adjusting for it would result in better standard error or not, that is something different from this scenario. We are just trying to identify based on the change in estimate method whether R is a confounder or not. All right, let us consider our second example where everything remains the same. Treatment effect is 1.3. Only thing that is different is our binary outcome variable. So instead of a continuous outcome variable, we have a binary outcome variable here. So here as well, R is a risk factor for the outcome, and R has nothing to do with A. That means R is not a confounder, right? So in this scenario, we again generate the data and our Y is binary, and that's why we are using the LogicLink with the Bunny-Hole family to get our logistic regression model fit, and we get 1.06 without adjusting for R, and with adjusting for R, we get the treatment effect estimate of 1.3. Now, in an empirical scenario where we do not know the original treatment effect estimate, and when we adjust for R and when we do not adjust for R, and we are trying to determine based on change in estimate method where R is a confounder or not, we would say that this is more than 10% change. That is why in a odds ratio scale, and that is why we should be adjusting for R, because R is a confounder by the method of change in estimate. However, the data, the way it was generated, R was not a confounder. R was a risk factor for the outcome, right? So when we are dealing with a scenario where our outcome was binary and we were using a logistic regression to estimate the treatment effect, and we were trying to determine whether R is a confounder or not based on the change in estimate, we were basically getting wrong results or wrong decisions in terms of whether R is a confounder or not. And that is one of the problems of the odds ratio estimate that we generally get, or the log odds estimate that we generally get out of a logistic regression model, that these odds ratio or the log odds ratio estimates are not collapsible. And what is collapsible or not is something that I'm going to explain in the next video. But for now, the summary of this video is that when we are dealing with a binary outcome and we are trying to estimate the treatment effect based on odds ratio, we essentially cannot determine based on change in estimate method whether R is a confounder or not, because there is something else that is happening. Even if we do not have any confounding, such as this case where R is a risk factor for the outcome, R is not a confounder, based on the change in estimate method, we would get a decision that R is a confounder sometime, even when R is not.